Based on what we've learned so far, when we're working to solve a linear system, we could employ one of two methods, either graphing or the substitution method, based on what we've learned so far. We'll discuss later on which methods might be more efficient to use given certain types of systems, but for right now, let's just suppose that if we're asked to solve the system, let's say that we choose to use the graphing method, right? So let's think about what we would need to do. Well, since both of these equations, this red equation as well as this blue equation, are lines, then it's usually easiest to kind of graph a line if it's in y equals mx plus b form. So let's solve these equations for y. So if we start with this first one right here, we'll have 4y equals 6x plus 15 when we add 6x both sides, and then divide both sides of that by 4. It's going to give you a final result when fully simplified of 3/2 x plus 15/4 is equal to y. So then there's an mx plus b form. We'll be able to graph it. Do a similar thing for the blue equation. So to solve for y, we can get this equivalent equation when we subtract 3x from both sides, and then divide both sides by -5. Negative divided by negative turns that positive, and another negative divided by negative turns that positive. So we get that equation as well. So now that we've got them both in slope-intercept form, or y equals mx plus b form, then you'd be able to sketch out a coordinate plane or use one that you already have and then graph these. But the fact that the y-intercepts there are fractions and decimals and such makes it a little bit more difficult for us to be precise in our graphing when we're doing this by hand. Of course, you could plug this into Desmos and then get your answer pretty fast. But we're just restricting ourselves to doing this by hand, so maybe graphing isn't necessarily the best, right? So if we were doing this and we had chosen a different method, so if we had chosen the other method that we know how to do, that of substitution, okay, then we know that substitution can always give you a precise answer because we're doing this just strictly algebraically. So we know that if we're doing substitution, you have to substitute into the other equation, given that you've isolated a variable from the first equation you've worked with. Just note that we've kind of actually done so with both of the equations. We've isolated a y. So let's say that I take the red equation where we isolated the y, and then from that, once you've isolated the y, then you can take this right here, since that's what is equivalent to y, and substitute it in for then y, but in the other equation. Then what we're going to get is that the 3x minus 5y equals a -13 becomes the following once we substitute. And it looks like I forgot to write the x, so let's sneak that in there. Okay, so now once we've done the substitution right here, we can solve this particular equation for x. So a little bit of distribution that can be done. -5 times that becomes that. -5 times 15 is -75. And then we still have 3x there plus -15/2. Okay, so we do actually end up with, in this particular problem, some like terms that are on the same side, both the 3x and the -15/2x. So if we think about this right here as being 6/2x, so we get the same denominator, then we can do the 6 minus 15 to give you -9/2x. And then -75/4 is equal to -13. Okay, so we're going to want to isolate the -9/2x, so we'll have to add 75/4 to undo the subtraction, and then add 75/4 to the other side. Then we'll have the -9/2x is equal to, so to add -13 with 75/4, we'll have to have common denominators, of course, to add the fractions. So when you find the common denominator of 4, you're going to end up with 13 times 4 is 52, so -52/4. So then when we add those two numbers together, 75 minus 52 is going to be positive 23/4. And then you can finally isolate and solve for the x if you multiply by the reciprocal of -2/9. And then we end up getting our final result for the value of x in this case, which would be -46/36, which I guess would reduce down to -23/18. Oofta. Yeah, so we got an interesting fraction answer, right? So there was a lot of work that happened, particularly in the area around here-ish. because when we isolated the variable, we got stuff that was like fractiony in nature, right? And then that resulted in all of this kind of cleanup work to really come up with what the answer for x was going to be. So it turns out that there are problems, especially in one like this, where substitution gets quite messy. And it would be nice if there was a way different than substitution to avoid this messiness that we encountered. And it turns out that there is. So I want to point out and help you make the observation that it became really messy because of right here where we had all these fractions and such, and that tends to happen a lot when you've got like numbers that are coefficients of the variables x and y that are not ones or negative ones. That'll tend to happen a lot. So what we can do to try to avoid some of that messiness, and that can be nice, is another algebraic method, which is that of solving by the elimination method. So I've typed up steps right there that you can use to kind of follow and read through. I'm just going to give those steps as I solve via example.